So now what we're going to do is we're going to introduce limits to this RRAM formula. And with those limits, we'll be able to evaluate this exactly. We'll be able to evaluate an integral and figure out its exact value without having to use a calculator. This is going to be very limited. It's not going to be able to do it for everything, and we'll talk about its limitations here in a minute. But it's going to allow us to do it with like that example that we just did, where we have we're evaluating the integral of x squared from 1 to 3 in that particular example. All right, so we just did this. We just said, okay, we've got this integral we want to evaluate. We want to approximate the integral. So we said that the integral from 1 to 3 of x squared with respect to x is going to be approximately equal to RRAM n, which we did some fancy calculations and had to remember some stuff from freshman year algebra and all that, and we ended up getting this expression right here. Okay, so we said that this integral is going to be approximately equal to this for any value of n. Now, the smaller that n is, the worse the approximation is going to be. So we said we want to make this really big. Well, it turns out, and the proof of this is a little bit complicated, and you don't have to understand it, but it makes sense that this would happen. But it turns out that the value of this integral itself, so the integral from 1 to 3 of x squared with respect to x, is equal to the limit as n approaches infinity of RRAM n, which in this particular example, I can replace this with this, and that's going to give us the exact value. So we can just take the limit as n approaches infinity of this rational function right here, and that's going to give me the exact value of this integral. Now, like I said, this is something that makes sense. Since our approximation gets better as we add more rectangles, it would make sense that if we could have infinitely many rectangles, then this approximation would become an exact value. But like I said, the proof is a little bit tricky. This was an assumption that was made for a long time before a proof was ever made for it. The key is the width of the interval has to approach 0. And when the width of the intervals approach 0, then the error approaches 0. And that's the key to the proof. That's like for more of an advanced analysis class than a Calculus 1 class. So we're not going to go through that proof. But what you need to know is if we can figure out what happens as n goes to infinity, then we can find the exact value of this integral, which is what we're all dying to do, right?